Okay, so let's pick up from where we left off. So we were talking about probability, and we will look through several of these uh, tree diagrams for analyzing, uh, probabilities of different events. And we have done enough of this to sort of, you know, come back and start to formalize some of the things that we have done. Okay. So, so we are going to do um, talk about probabilities associated with sets, and what we will uh, notice is that several of these the rules that we define for probabilities is going to be basically very similar to the rules that we have for counting the sizes of sets. Okay, so uh, so we are going to talk about probabilities associated with sets. So so basically we start with a uh, non-empty countable set. Okay, and we call that as a sample space. Okay, because this is sort of uh, if you think of an experiment with many outcomes, then each of these outcomes corresponds to one of the elements in this set. Okay, and so again, an outcome is simply an element of this set. Okay, and then we can define a probability associated with each of these outcomes. And for the function to be called a probability, there are a couple of uh, restrictions. One of them is that the probability is always has to be positive, right? So it can be it has to be greater than or equal to zero for all uh, elements of the set. And in addition, the probability has to add up to one. Okay. Can I see a few more of you? Yeah. So I'm not exactly keeping track of. Um, there's a question on chat. So there is. I'm not exactly keeping track of who is in the class, although it's something that I have. The information is there. I can look at it later. So if you are not able to make it occasionally to a class, well, that's you know, I guess that's the difference between college and high school, right? So you have the if you choose not to show up, then that's entirely up to you. So don't, in any case, don't have to worry if, let's say, you have some, you know, you have a reason not to show up, then that's fine. Okay, so what I want to add to that is the notion of an event, right? An event is simply a subset, right? So we have, if the sample space is a set, then this event is simply a subset of this uh, set. And then we can associate a probability with this event, and in a very natural way, which is to say you take all the events, all the outcomes, or all the elements of this set, right? And then you add up their probabilities, and that gives you the probability of the event itself. Okay, so that's the definition of an event probability in this context. Okay, so once we have this definition, we can very easily, you know, um, see why many of these other rules make sense. So if you take disjoint sets, right, we can draw their Venn diagram, right? So there is the universe, right? The universe is the sample space S, and then there are these subsets E1, E2, up to En, right? So they are disjoint, therefore, they are not overlapping in any way. right? And if you want to add up, um, so we know that if you define an event E to be then we know that the cardinality of E is nothing but the cardinalities of right. So since what we do in in order to look at the probability of the event, we simply go through the elements in the set and we simply add up the probabilities of each of those elements. And so it is very clear from that way of defining the probability of events that when you have disjoint events and you take the union, their probabilities are simply going to add up, and that's what this rule says, right? So there is really nothing that you need to understand specifically about probability in order to uh, uh, you know derive this rule, right? At the same time, so the rule follows in a very straightforward way from the definitions we had in the previous slide. On the other hand, if you apply what you know about probability, then the results we get certainly agrees with that, with what we know. Okay, so now let's look at another rule, which is the complement rule, right? So this is again very easy to understand from the Venn diagram, right? So once again, you have the sample space S. This is A, right? And then what is outside is the complement, right? So this is A bar, or the complement of A, and it is very clear once again from how we define the probability of the event A bar, right? So the probability of the event A bar is obtained by simply adding up the probabilities of all the points that are outside the circle, right? And if the points all over the inside this rectangle, that if they add up to one, then the points outside the circle are going to be given by one minus whatever is inside the circle, right? So the complement rule again follows from what we know, how we have defined the probability in terms of set theory, and once again the rule itself, where we essentially compute the complement and then do a one minus of that, right? That's a technique we have used often in when we deal with uh, either counting or probability, and once again, it's consistent with this definition. Okay, so same way if you take B minus A, once again, right? So right, so if we have, so this is A and this is B, then so uh, hmm, I guess let me just, right? So we can see that B minus A from the Venn diagram is the same as B minus A intersection B, right? So uh, so it's easy to see why this rule follows, because b minus a is simply b minus a intersection b, and and therefore we can simply subtract the probabilities corresponding to the points that are all the outcomes that are situated in this intersection area, and then we will get the probabilities of the outcomes that are purely within the B part and not inside the A part, right? So that's what this rule says. And then there are like the the inclusion exclusion rule for counting that can again be applied to uh, uh, you know uh, probabilities, and the union bound is simply the a special case of the inclusion exclusion, where we are saying that, hey, this, because it's a probability, it is always going to be positive, and therefore from this equation, right, we can easily derive this one, because what we did was we went from this equation and then we took away here we are subtracting something and that's not being subtracted here, so essentially the right hand side, we have made it bigger, therefore this equality is now going to become less than or equal to, right? So there is this simple way of deriving all these rules from what we already know about set theory. So let me stop here for a second and see if there are any questions about uh, what we have covered so far in this unit, or about your homework.
I have a question.
Yeah, go on.
Uh, I recently saw a new part for the homework. For homework 4 has been added, like where we could submit a PDF file of it.
Yeah.
Do we only have to submit a PDF file, or should we submit both?
So follow the directions that are there on Blackboard.
Oh, I didn't see it. All right.
Right? So it says exactly what I want you to do. And I prefer not to say things twice,
Okay.
for the reason that whenever I say things twice, there is a chance of saying something inconsistent. And uh, so if it is about the material we teach in class, then it's one thing. But on the other, if it's about deadlines or some procedure for submission, I prefer to just put that down in writing, so it's there is less of a chance for misunderstanding. Okay. um, any other questions? Okay, so
Just
yeah, go on.
could you go over the union bound one, right? That says
Yeah.
union of A and B, the probability of that, because my confusion is that A and B is that entire probability space, right? Of chance of A happening or chance of B happening. Can that be interpreted likewise?
So again, if you draw the Venn diagram, right?
Right.
So right, so we can write right. So this is a familiar Venn diagram, right? So we know that if this was the case, then we know that the cardinality of A union B is
All right.
22, right?
Right.
Whereas the cardinality of A plus cardinality of B will be 27, right? Because this,
Oh, I
the
understand.
middle part will get counted twice, once as part of A and once as part of B,
All right. Thank you.
right? So it is this difference, right? So and that's why in the inclusion exclusion rule, we back out the intersection part once, because the intersection part is going to be counted once on the side of A and once on the side of B. So we cancel that out over here. But if you don't do that, then of course you're going to double count something, and therefore it becomes less than or equal to, right? Of course, it can never be the case that A union B has more elements than what is on the right hand side.
Thank you, Professor.
So okay, let's. Okay, so there's just one more rule, which is also fairly easy to understand. If A is a subset of B, then, and this again follows, very much from, you can again draw this diagram, right? If A is a subset of B, then that could be your B, right? And let's say this is A, right? So now we can say that, because probability of B in this case is very clearly, we can just add up these two probabilities to get the probability of B. So this is going to be probability of A plus probability of B minus A, right? And so we can very easily say that so probability of B is going to be the probability of A plus some quantity, right? So therefore, we can say that if A is a subset of B, then probability of A is always going to be less than or equal to probability of B, right? So again, all of these can be understood very easily by just simply drawing the Venn diagram. So very often we work with what are called uniform probability spaces, right? And what that means is that we are going to consider all outcomes as equally likely, right? Which means that the probability of every element in the sample space is equal, right? And once we say it is equal, then that follows that so by convention, we use a square bracket for probability. So probability of omega is 1 divided by the size of the set, right? Size of the sample space, right? Because once we say that it is the outcomes are the probabilities of all outcomes is going to be the same, and you combine that with the condition that when you add up the probabilities of all outcomes, it should add up to 1, then you immediately get that the probability of each outcome is 1 divided by the size of the set. And since the probability of an event E is obtained by adding up the probabilities of all the events, all the elements in the set, right? So from this, we can derive that probability of an event is going to be given by the number of elements in the event divided by the total number of elements in the sample space, right? So any questions on what we have done so far? Okay, so I assume this is fairly easy to follow. So so we said the probability spaces are countably infinite, right? So the countably infinite condition means that we are talking about discrete probabilities, right? So very often you work with continuous probabilities, which means that you work over a set such as the set of real numbers, right? So those sets are uncountably infinite. Okay, so when we talk about continuous probabilities, what we are talking about is working in with uncountable sets. So when we say we are working with countably infinite, that means uh, another way of saying that is that we are working with discrete probabilities. Okay, so now so far we looked at a few examples. All of them were finite sets, right? And not only finite, uh, you know, it is very uh, small, right? But sometimes you come across infinite probability spaces, as in this game, right? So two players take turns flipping fair coins. The first one to land heads wins, right? So what's the probability of each player winning? So can you uh, guess the answer to the question? Not the exact number, but in terms of you know the what which probability is greater, right? So do the two players have the uh, exact same chance of winning, or is there a difference?
Well, I think the first player to flip has a big advantage because they could just win on the first try.
Right, right. So although yeah, again, we are making this assumption that we are making this uniformity assumption, right? So we're going to assume that all the coin is fair and all outcomes are equally possible, right? But even then, the person who goes first is going to have a better chance because they have a chance of coming up with the heads on their very first attempt, and then they have won, right? So we can draw the tree diagram again, right? So we can say, uh, so again, the first, so the very first action is by the player one, right? And it could be a heads with the probability half, and it could be tails again with the probability half, right? Now, if it's a heads, right? So the player has won already, right? So in this case, if the player one comes up with tails, then player two has a chance to go, and so you're going to have heads and tails, and this is going to be the player one is going to lose, or I'm sorry, that's so if both tosses come out with the tails, then player one goes again, and once again you have uh, heads, there is a win, and tails, they have to continue, and then heads is going to be a loss, and so on, right? So we can then say, okay, let's look through all the W nodes and add up their probabilities. So that means, so here the probability is half, right? And for this node, you have to look at, so 1/2 times 1/2 times 1/2, right? So this is 1/8. And once again, 1/2, 1/2. So this is 1/32, and so on. right? So you can see a pattern emerging. And so the probability of first player winning equals 1/2 times 1 plus 1/4 plus 1/16 plus, right? And so that is a geometric progression. So right, so substituting the formula for geometric progression, then we get basically, so this numerator will become 1, right? When because you raise it to power infinity, then this is just going to become this fraction, 1/4 to the power infinity is just 0. So the numerator becomes 1. The denominator 1 minus 1/4 is just 3/4. So the result, no, sorry, this is, yeah. So so you divide by 3/4, which means that you multiply by 4/3. So the first player has a 2/3 of a chance, to 2/3 probability to win, whereas the second player obviously he can win, but only with the probability of 1/3, right? Any questions? Okay, so again, if you don't ask any questions, then we'll make progress quickly, probably too quickly. So so now so that brings us to the main topic that we have been building up to cover, and that is the notion of conditional probability, right? Which means that we want to talk about the probability of an event given that we already know something. Okay, so so the condition is something that limits the what event or what subset of outcomes are possible. Okay, so so the condition is you can think of it as another set, okay, a subset of the sample space. Okay, so that the condition is essentially a subset of S. And the conditional probability, what it is talking about is it says that instead of thinking that the set S, the probabilities are going to add up to 1 in the set S, we are going to now instead think that the probabilities are going to add up to 1 in this subset C. Okay, so so the conditional probability is given by this formula, and what it says is once again we can understand this using a Venn diagram, right? So here is X, and here is Y. Okay, so under the condition 1, okay, which means that uh, the so this is the notation we use for saying what is the probability of X under the condition Y, right? So the way we define this is by saying that, okay, whatever is in Y, right? So that is the probabilities of those points inside Y, right? We are going to think that that assume that probabilities of things inside Y is going to add up to 1, and everything else adds up to 0, right? So the X is maybe poor choice. So let's say the pluses and minuses over there, right? So the probability of pluses and minuses, right, is going to be 0, right? So we are just saying that only the points inside Y, right, are going to have a non-zero probability, and everything outside, like here and like here, it's all going to be 0. Okay, so now what is the now if you ask what is the probability of A, you know that, or rather X, then you know that this part of X, right, we have already defined that this part contains nothing, right? The probability adds up to 0. So the only probability of X is going to come from this part, right? So that's why we have that X intersection Y appearing. And the effect of saying that probability of Y equal to 1 is obtained by simply dividing this area, right, by that area, right? So that's what we are doing, because Y is everything. And so if we divide this area by that area, that tells you, gives you this conditional probability. Okay. So let's um, so that's how we arrive at this formula, which basically says, look at the intersection, because we know that Y is already true. So once you know that Y is already true, what is the likelihood that A is true? You obtain that by basically taking this common area and dividing it by the whole of Y. Okay. So so let's take an example. Let's go back to our game, right? The game show. So and let's take an example, right? So this is although we analyzed the game show, we didn't quite answer why there is this confusion that we have. Our intuition says that it shouldn't matter whether you switch your choice, but in fact, the analysis shows that by switching, you have a much higher probability of winning. And we are going to try to understand that using conditional probabilities, right? So let's take an example of a conditional probability. So one of them is that the contestant picked the gate A, and there is a goat behind gate B. Okay, so given this condition, right, what is the probability that the player can win by switching choice from gate B to gate C? Okay, so Uh, so once again, what we need to do is that this is going to be one set, right? So this is going to be another set, and we are simply going to use this formula to estimate the conditional probability, right? So what does the conditional probability tell you? It tells you whether, given the information that you know, right, does it make sense to switch or not, right? So let's say this is the information that you know, right, that you as the player has picked the gate A, and there is in fact a goat at gate B, right? So given this information, right, what can you say about the likelihood of winning by switching, right? So we are going to simply take, list the sample space, and then identify what this event corresponds to, or rather, what subset of the sample space is given by this event, and what sample space is given by this event, right? And then, so so what we do is that we are saying that the contestant picks A, and there is a goat at gate B, that corresponds to these three outcomes, and the contestant wins by switching, right, on these six outcomes. Okay, so I'm going to flip back to I don't think yeah, I'm going to flip back many slides to look at what it, to at least point out that this set has three elements, and this set uh, where you win by switching has 1, 2, 3, 4, 5, 6 elements. Okay, so let's go back to, so we're getting there. Okay, so we already marked what are the outcomes that correspond to you know uh, winning as a result of switching, and you can see that there are 6 tick marks, and I told you there are 6 outcomes, and although you can't see these two side by side and verify that it is exactly these 6 that I've written down, you can sort of take it, you can go back and look at it uh, later on, and convince yourself that these are the exact 6 points that I have picked and associated with the event of winning by switching. Okay, now let's look at the other event. So what was the other event? I know it's obvious, but I want to make sure that uh, people don't go to sleep. So what was the other event that we were looking at?
Picking A and the goat
Greg?
at B. Oh,
Picking A and having to go to B.
Right. So the player picked uh, gate A, and there is a goat behind gate B. Right. So so you can see that that's one case where the player picked gate A. The other case where player picked gate A, and this is the third case where the player picked gate A. Now we have to see which of these have a goat behind door B. So this one, right, because gate B is being opened, right? Or you can look at it this way, that the actual car is at location A, right? Therefore, there is in fact a gate a goat behind gate B, and there is a goat behind gate B, right? Gate C, right? So so the point is that in this particular path, right? Both of these outcomes, right? Uh, you still have a goat behind gate B because the car is actually behind gate A, right? So both of these outcomes correspond to a situation where the uh, player picks gate A and there is a goat behind gate B. Okay. So now looking here, the second case where the player picks uh, um, gate A, you know that the car is behind gate B. Therefore, it's certainly not the case that there is a goat behind gate B, right? So none of these three outcomes or four outcomes, correspond to a goat behind door B. If you come down here, right? So you can see that if uh, 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 the if the car is behind gate C, right, and the game show host opened gate B, then clearly there is a goat behind gate B, right? Uh, and so okay, so those are the cases where so notice that these two kind of don't count, right? Because these two do not correspond to the player guessing the door A, right? So what we are looking for is a condition where the player picks door A and then there is a goat behind door B, right? So that's why we end up with just these three cases, right? So this one is not included because there is a car behind door B, and these are not included because these don't correspond to the player picking the door A, right? So because we have put both conditions, we end up with just three cases where the player picks door A and and there is a goat behind door B. Okay, so let's go back to where we were. Right? So now I took those 6 outcomes where you win by switching and asked what is the probability of these 6 happening, given that these are the ones that are true, right? So what we can do immediately is that remember this picture, we are going to take sort of what is in the intersection, right? So that's this part, right? So we're going to look at the probability of what is in the intersection and divide it by the probability of uh, uh, the whole y part, right? So the whole y part here corresponds to 3, right? And the intersection, if you look through, you will find that there is only one element, right, that is common between this set and this set. Okay, you can go through that carefully, but you'll find that there is just one element. And so so the numerator in this is simply, this one has size 1 and y has size 2, but that's not the point. So I'm sorry. So let's just, that's a distraction. The size doesn't matter. We have the probabilities of these two events that we calculated before. And, again, you can go back and look at it. So you will find that the probability of this event, this outcome CAB, happens to be I believe. Okay, so let's just go back to um, calculating. I guess there's no sense in me telling you. So let's just remember what is CAB, because these three we have already marked on the picture. So let's just go and see what is the probability of CAB. Okay, so the probability of CAB is 1 by 9, right? So the numerator there is 1 divided by 9. And the probability of these three outcomes that are in the denominator, they add up to 118 plus right? So this is 1 divided by 18, 1 divided by 18, 1 divided by 9. So if you do the addition, then you have 1 divided by 9 in the numerator, and this will become 2 divided by 9, right? So when you add 1 by 18 plus 1 by 18, that becomes 1 by 9. So 1 by 9 plus 1 by 9 is 2 by 9, right? So in other words, the probability is half, right? So what does it tell you? So now that you know that this is probability of half, so that tells you switching doesn't help, right? Because you might as well not switch, right? Because switching versus staying on the same with your choice doesn't help you, right? And it kind of matches your intuition, because whether once you know that there is a goat behind door B, right? All you know at that point is that the car is either behind door A or door C, right? There is no reason for you to say that there is a bigger chance of the car being behind door C versus the car being behind door A, right? And therefore, in that situation, given this is the information that you know, right? You have picked A and there is a goat at door B. There is no reason for you to have a higher probability of winning by changing your mind from gate A to gate C, right? And this is sort of our intuition, and this is why we find this whole example confusing or intriguing, depending upon how you look at it, right? So what's wrong, right? So what's the problem? Because our analysis is correct, and it tells us that you should switch, but why is it that we are finding that, why is this analysis telling us that switching doesn't help, while the analysis that we did the other day told us that you win by switching? What could be going on? Anyone? Frederick.
I think it's because we're just not accounting for all the cases. I think if we pick A and the goat is at C, we should get the same thing. But if we pick A and the goat is at A, we should have a higher chance of winning by switching. So we need to account for all of that, I think.
Okay, so you could be saying the right thing, but the main point is that this is the wrong question to ask. Okay, so it is definitely true that if the information you have is this, right, then it doesn't really help. right? To know to switch, right? If this is all you can say, then it's certainly true that A and C are equally likely to have the car, right? But this is not the information that you have, right? The information that you have is slightly different. And what is it? You are the, if you are the contestant, what is the information that you have to make a decision? So you picked A, so obviously that part you got it right, right? What is the second piece of information that you have? Is it that there is a goat behind B, or is it something else?
If the door revealed is B?
Right, right. So that's the point, right? So there is, by just looking at what is behind the goat, I mean, what is behind the door B, we simply, are overlooking the actions of the host, right? Because the host picked door B for a reason, right? And then if we take that into account, then we will have a slightly different analysis. So let's do that, right? So you pick A and the host opens B, right? And now you no longer have three possibilities here, right? So in fact, you have this and that's this, but this one is no longer here because you can see that this particular outcome corresponds to you. The car is behind A. The contestant has picked A, right? And the host has opened C, right? So since the host opened C, this condition of the host opening B is not applicable, right? So as a result, this particular outcome is no longer in this set of you picking A and the host opening B. And so now what you have done is you have reduced the uh, uh, the denominator in your calculation, right? So previously you had this as the denominator, and since you eliminated the middle one, you end up with the denominator as 1 by 18 plus 1 by 9. And then if you do the math now, you end up with 2 by 3 rather than 1 by 2, right? So this explains to you why there is this confusion, because often we are not, when we think intuitively, we are not sure whether we are thinking about this question or this question, right? So we, if we omit the host's action and simply look at, what is, our choice and what is behind door B, then we might end up analyzing the wrong problem and arrive at the wrong probability, right? But if we look at exactly, what the host is doing, then we will come up with the correct analysis and say, yeah, so, you know, um, so the main point being that if our choice of gate A was right, okay, then the probability that the host will open gate B is somewhat lower, because if we made the right choice, the host has the equal likelihood of opening either B or C, right? And as a result, the probability that we are right and the host opens gate B is somewhat lower than when we are wrong and the host opens gate B, right? So in an indirect way, whenever the host opens door B, there is a little bit of a clue that maybe our choice of gate A was wrong, right? And that's why we should switch, right? So the host is really indirectly giving us a clue, because if our choice of A was correct, then they are much less likely to open the gate B. Okay, so so let's go back and look at the picture again so we can understand, right? So AAB and CAB. Right, so those AAB and CAB, right? So in this case, right, so where we have already made the correct choice, right, the probability that the host opens door B is only half of the probability that the host opens door B, in this case where we have made the wrong choice, right? So when the door B is being opened, we are much more likely to be in this outcome than in this outcome. Okay, and that's why we have to say, hey, why did this happen? Maybe it's more likely that the car is behind door C. Any questions? Okay. Nobody wants to say anything today. Quiet day. Okay, so so now that we have seen the Monty Hall problem as an exercise in conditional probability, because that's sort of what we were trying to get at. Now let's look at another problem to illustrate conditional probability. Okay, so so let's say that there is a playoff between two teams, right? And the teams are matched. So when they play the first game, there is a 0.5 probability for each team to win the first match. But what's going to happen is that if a team wins, they are going to be energized, and in the next game, they are more likely to win, right? So the winning team has a 2/3 probability of winning the next match, right? Similarly, the losing team has a higher chance of losing because they feel, diffident going into the next game, right? So now we can ask the question, what is the probability that the team that wins the first match will win the playoffs, right? So this is a question that, each time, if those of you who follow playoffs, this is always a question, hey, our team won the first match. What is the likelihood that, they will win the series, right? So we can analyze it using the same old tree diagram, right? So this is the first match, game one. So team one can win. And if the team one wins again, then the series is over because it's a best of three, right? So if the first team wins the first two games, then the series is over, right? Otherwise, there can be a loss, and then they can come back to win. But what you see is that in the first game, the probabilities are half and half. But once you are here, the winning team has now a 2/3 probability of winning the second game and only 1/3 probability of losing. But if the first team loses the second game, then the chances of them winning the third game is only 1/3 because they lost the previous game, right? So this is the tree that basically summarizes what we said here. Okay, and now what we are asking is that suppose you are here, right? Then what is the likelihood of ending up with one of these two outcomes, right? Because these are the two outcomes in which the team one wins, right? And we are asking that, given that team one has already won the first game, that is where you are, what is the likelihood of reaching one of these places, right? And so we can so what we have done is we have done our usual thing, marked off the events, the event that A wins the series. These are the three events, three outcomes in which the first team wins. And these are the three outcomes corresponding to when the first team wins the first game, right? And then all we are doing is we are applying our conditional probability formula, right? Which basically says first take the intersection of A with B, which means those two, right? So this is no longer in the intersection. So what we are asking for is the probability of these two outcomes divided by the probability of these three outcomes, which means 1 by 3 plus 1 by 18, right? So those are the probabilities of these two outcomes divided by 1 by 3 plus 1 by 18 plus 1 by 9, right? So if you do the arithmetic, the numerator, this is going to be, I'll write on this side, this is going to be 7 by 18, right? So if you change the denominator of 1 by 3 to 18, then the numerator will become 6. So 6 plus 1 is 7. And here, once again, 6 plus 1 plus 2. So this will be 9 by 18. So the answer is 7 divided by 9, right? So this is, did I get it right? Yeah, so 7 divided by 9 is the probability. So we can, again, work through our 4-step method, which involves finding the sample space, defining the events of interest, and finding the probabilities for all of the events, and then using the conditional probability formula to calculate the probability, and that says 7 by 9, right? So the moment some team wins the first game, there is a much better chance of winning the whole series, right? In real world, there is certainly an effect of winning, right? So the team that wins certainly tends to have a slightly higher chance of winning the next game, but it's not so skewed, right? So I don't think in real world the probability of winning goes quite as high as this. Okay, so there are a couple of more rules that I want to talk about that relates to conditional probability. One of them says that the probability of E1 intersection E2 is the same as probability of E1 multiplied by this conditional probability. And this is obvious because we have said PR of E2 given E1 is nothing but probability of E1 intersection E2 divided by probability of E1, right? So now if we take this over here, then we have probability of E1 multiplied by probability of E2 given E1 equals probability of E1 intersection E2, right? So this is where this rule is simply a different way of stating the definition of conditional probability, right? So so again, you'll find that all these rules that we talk about in probability are just so straightforward from the definition, right? So, and this can be extended to the case of three-way intersection. So you multiply the probability of E1 with the probability of E1, E2 given E1, and then this, right? So, and the Bayes rule is, this is again an application of the definition of right. So similarly, we can write probability of B given A equals probability of A intersection B divided by probability of A. Now, if we take this over here and take this over here, right? Then notice that what you will have on the right-hand side is the same, right? Is probability of A intersection B. So, which means that PR of A multiplied by PR of B times A equals PR of B multiplied by that, right? So, so if we take these to this side and equate them, then we get PR of A given B multiplied by probability of B equals probability of B given A multiplied by probability of A, right? And now if we take this over here, right, then we have exactly that formula, right? So once again, just simple arithmetic manipulation, and we get this third rule, which is called as Bayes rule. And yeah, so there are a few more, such as inclusion, exclusion, and so on, which can also be derived in the same way from the definition. And before we conclude, let's talk about independence, right? So in probability, we very often talk about independent events, and one of the ways, one of the things that we do with independence is that if two events are independent, the probability that they occur together is obtained by simply multiplying the probabilities, right? So this is one of the most basic rules involving probability that we have known for a long time. And but this is applicable only when the events are independent, right? So what this definition says is that whenever this is true, that also implies that the events are independent, right? And it also says that if the events are independent, the conditional probability of A occurring given B will be exactly the same as the probability of A occurring on its own. And once again, this can be obtained from our definition of conditional probability, right? So right? And now for independent events, PR of A intersection B is nothing but PR of A times PR of B. Right? And so now we can subtract, we can cancel out PR of B from the numerator and the denominator, and we get PR of A given B is PR of A, right? So, so if the events are independent, then from the definition of the conditional probability, we can derive that the probability of the conditional probability is no different from the uh, unconditional probability of the event A itself. Okay, so so but one thing to keep in mind is that generally independence is an assumption, right? So we typically assume that the independence is fairly easy to, I mean, it's an assumption, although there are experiments you can do to try to see whether independence is the assumption is justified. It is really ultimately going to be an assumption, not something that can be proved. Okay, so the last thing we want to talk about is uh, another interesting case that happens that occurs commonly with medical testing. Okay, so let's talk about so this is an application of conditional probability. So let's talk about define some concepts and then introduce the problem, right? So false positive means that so there is a diagnostic test for diagnosing a medical condition, right? So for instance, you can think of COVID test, right? So so the false positive is the likelihood that you have someone who is not sick, right? But there is but the test says uh, you know the test comes back positive, right? So that is a false positive because the person really is not sick. Okay. Similarly, false negative means the person is actually sick, but the test says that you're not sick. So if you're following the COVID tests, right? So there are two tests. One is called the PCR test, which is the slower test that takes a couple of days for the result to come back. It has low, false negative, very low false negative rate. But then there is also a rapid test, which comes back within 15 minutes or half an hour or something like that. But that has a higher false negative, and you I'm sure you followed the news about Trump getting COVID, and how that was traced back to the fact that these rapid tests have higher false negatives, and therefore he was exposed to uh, you know people who are sick. But anyway, that's besides the point. So what we are trying to understand here is, what do these false positives and false negatives mean in the context of someone getting tested, right? So consider a diagnostic test with a false positive and false negative probabilities of 0.05 and 0.02, right? So the likelihood that somebody who who's not if you do a test on a random individual, right, and if it comes back positive, then the likelihood that this random individual does not have the disease, right? So that's the definition of false positive, right? So you pick a random individual, you give this individual a test, right? If the individual is not sick, then the test has a probability of only 0.05 of coming back positive, right? Similarly for false negative, right? So suppose, one day you get up and, let's say you are, coming back into the dorm, and they are asking you to supply a COVID test, right? So let's say this is about COVID, right? And you go back and the test comes back positive, right? So what is the likelihood that you actually have COVID? Right? So I have given you, seems like I've given you all the information that you need, right? So you're not, you don't know if you're sick, but clearly, you are doing this because, the university requires you to do it, not because you are actually feeling sick or anything like that. So you are one of those random individuals that have been selected to undergo the test, and you get the result back. It says, hey, you're positive, right? So what is the likelihood that you're actually have this condition, right? So let's not think too much about COVID, and then because that can muddle the picture. But the point is that you took the test and it came back positive, and what is the likelihood that you have that condition?
Is it 95%?
That's this number seems to suggest that. Is there a different answer? Anybody else wants to say there is the answer is different? So the answer is that it depends. You can't tell. Okay. Now, what does it depend on? It depends on what fraction of the tested population is actually sick. Okay. So we can understand this very easily using our tree diagram, right? Let's say that only 1% of the tested population is actually sick. Okay. So this may not be applicable to COVID, but there are many routine screenings that people go through where the population that undergoes the test that's likely to be sick is very, very small, right? So let's draw our diagram, right? So so this is sick, not sick, right? And this is 0.01, this is 0.99, right? And then positive, negative, positive, negative, right? So so this is the person is sick, right? And it comes back negative, so that's a false negative, right? So this is going to be, given the information that we have, this is 0.02, which means that this is going to be 0.98, right? Similarly, you are not sick, so if you are positive, right, that is going to be a false positive, which so this is a false positive, so this is going to be 0.05, and this is 0.95, and then let us calculate the leaf probabilities. So we multiply 0.01 by 0.98, so that is 0.0098, and this is 0.0002, and this is 0.0495, and this is 0.94, let's say. Okay, so I'll approximate, right? 0.99 times 0.95, I'll say is 0.94. Okay, so now what we are asking for is that the test came back positive, right? So this is the condition, right? So we are asking what is the probability of being sick, right? Which is this node, right? Given that the condition came back, the test came back positive, and what you get is this node, right? So so you get a formula such as 0.09 divided by 0.0495 plus 0.0098, right? So because remember, what is the conditional probability? We take the intersection of this event that you are sick right? With the two events or the two outcomes where the test comes positive, and you can see that the intersection is going to be all of this because and then you do the calculation and you arrive at a formula that's approximately this. There may be some differences in the second digit or third digit or whatever, right? But you can see that when you look at it very quickly, you can kind of ignore this as compared to 0.0495, right? So at least to get a quick estimate of the value, and then you end up with something like 0.01 by 0.5, which is like 20%, right? So the likelihood that you are sick is in fact quite small. Okay, so so this is one of the problems with a lot of medical testing, that even though the tests themselves are accurate and they have a very low false positive rate, the problem is that the prevalence, the condition, the prevalence of the condition in the population is so much rarer than the error rate of the test, and therefore you end up with a situation where the even a very good test ends up producing a lot of false positives. Okay, so that's really what I wanted to say today. We went over time a little bit, but on the other hand, I didn't want to leave this topic on this very last slide. So that's sort of ends this unit on probability, and we are going to switch to a different topic from the next lecture onwards. Okay. Okay, very good. So if you have any questions, ask away, or else feel free to drop off and go do what you need to do. Okay, good. Thank you.